I want to do a little bit more of a close analysis of what's going on and all that information we get when we do the regression calculation in Excel. So I want to go back to the example about shipping costs. Problem number 31 from the textbook. Number of orders versus total cost to ship. And I can do scatter plot and create a regression equation and an R-squared value. Now again, simply extrapolating from the information I've got, the intercept here, negative 31, that's not very useful. I don't know how to have a shipping cost that's negative. I'm going to pay you to take my product here. No. And the slope here would mean that for every additional order, they expect the shipping cost to rise by approximately 493. Okay. R squared is 0.67. What does that tell you about the fit here? What does R squared tell me? We gave it a name.
Yeah, percentage of stuff.
Right, it's how much it's determined by. We called it the coefficient of determination. And it says that 67% of the variation in shipping cost is strictly due to order size. So 2/3 of your shipping cost can be traced directly to how much did you order. The other third might be things like distance, fragility, insurance, etc., but that's not mentioned in this correlation because we're only looking at one factor. But if I do the big version of the regression using the data analysis, then I get all this junk. There's a lot more here. R squared, 0.67, that's the same 67% we saw on our previous screen. R squared right here. It also allows me to take the square root, get R value itself, the Pearson correlation coefficient. The closer that is to 1, the better, more straight line this data is. But I've got all this, it says ANOVA. It's measuring variability from our predicted dots on the line to where the dots actually were. And this is where we get a p-value. What are we testing with a p-value? What's the significant thing we're looking for here? We're looking to see, is our slope different from 0? How confident are we that this data reflects the actual slope as opposed to thinking not could be 0? We do this with a confidence interval as well. Over here, the confidence interval, 95%, variable 1, that's our slope. Right here, confidence interval goes from 2.5 to 7.36. 0 is not in there. I should be confident this slope is not 0. My p-value should be below 0.05. And it's way below 0.05. Notice that in this test, they don't actually label it P. They label it the significance of our F score. P is a measure of significance. So significance F. Normally I would compare a calculated F value with a critical F value. it didn't automatically provide me with a critical F value. I can use the F table to look that up. F dot inverse 0.05. I can do that same degrees of freedom in each direction. I can do that whole setup. But it just gives me 20.45 as a calculated F. That's way out there on the change when we look at that picture for the F curve. But I really don't think that's helpful to me without the F calc somewhere in here. I prefer to use the p-value, but they've labeled it significance of F. At 0.001, that's way smaller than 0.05. Yes, our slope should be way away from 0. The larger our F score is, the better this fit is going to be. I still should have a critical value to use the F table to look stuff up, but Excel should be able to get that for me. I have to actually ask it for it. It won't automatically provide it in here. I could graph a confidence interval around our line. I could go to each spot on the line and graph above and below the appropriate confidence interval and get 2 more parallel lines. For the most part, I don't think that's helpful. But when you see error bars in a scatter plot or in a prediction, that's what they're graphing. Graphing that sort of confidence interval. I think it's a little more helpful to actually ask, how far out of line are we? Are any of these data values particularly strong outliers or particularly unusual? We had a definition for unusual and outlier when we did standard deviation. I think I mentioned this on Wednesday. What was that definition? Data value is unusual if a data value is an outlier if what's over or under 3. Which would make the z-score above 3 or below -3. 3 standard deviations away from the mean. That's our outlier. Unusual was 2. So 2 standard deviations and out is unusual. 3 standard deviations and out is outlier. What's standard deviation? I've got a standard error. That's not the same thing. I don't have a standard deviation here. So I need a different way of determining my differences. So I'm going to go back to this data, and I'm going to do the regression calculations in Excel again. Data analysis, regression. Okay, the Y values are here. The X values are here. I put labels in the top row. Now this time, notice there's a whole bunch of boxes down here at the bottom. And this first box here says residuals. And it gives me 4 options. I'm just going to check them all for the moment. The one underneath it says normal probability. We'll talk about what that means as well. I'm going to check them all. I want all of these. 1, 2, 3, 4, 5. I'm still doing a 95%. Oh boy, I got a lot of stuff here. Okay, I've now been given a bunch more information. Everything up here is the same ANOVA and regression information we saw earlier. including the confidence interval, the significance F, our p-value, all of this is the same up here. But now I have more residual information. Okay, the hell is this? What was our definition of a residual again? Say again? That's our coefficient of determination. That's our R squared. Now I'm looking at the residual for each data value. Remember, our scatter plot makes a prediction for each x value. The x value, 767, should give me a certain y value. The x value, 677, should give me a particular y value. That's the y value that's on my line. The actual y value is the one that's over here in my data chart. 677, the y value is 3673. That's where this dot is. But notice that's not where the line is. Residual is the difference between the two. $677 was the 10th piece of data. If I go to number 10, the residual is 365. My predicted value, instead of being 3,600, whatever the hell it was, is 365 higher, lower. Which way? Let's go look. The dots above, actual minus predicted. Y minus Y hat. So my predicted value is 365 lower than my actual value is. Or if you want to think of it the other way, the actual value is 365 bigger. That's why it's a positive number. Some are positive, some are negative. Some of these are pretty big, some of these are pretty small. But now I have a list of single value data. Let's just look at that column, the residuals. Outside of this piece of paper, outside of this spreadsheet in the background, it's going to calculate the standard deviation for that group of 12 numbers. For this group right here, it's going to calculate the average and the standard deviation. And then we're going to get a bunch of z-scores. Those z-scores are called the standard residuals. So now I have the ability to say, are any of these unusual? Are any of these outliers? Because now I have z-scores. I've standardized my data. So in this case, are any of my residuals large enough or small enough to qualify as either unusual or outliers? Nope. Nothing's bigger than 2, nothing's smaller than -2, nothing's unusual. Therefore, nothing can be an outlier because those would be even further away. Huh. But residuals even tell me more than that. Because we made an assumption when we did our regression behavior. We made the claim that whatever error existed should be normally distributed with an average of 0. We are just as likely to be low as high, just as likely to be a little bit in either direction, and it should look like a normal distribution. And that all of the errors are independent of one another. There's no mitigating, compounding, confounding factor or confounding variable involved here. And that's what these pictures help me understand. So this very first picture, I'll blow it up, make it a little bit bigger. This just plots the residuals. Graph goes minus 1,000 to 1,000. It's not standardized. It's just the residuals. The raw numbers that show up in this column. And my question is, when I look at these residuals, does this data have a visual pattern to it? Is it going out as we go from left to right, getting further away from zero? Is it coming in as we go from left to right? Or is it, equally as we go from left to right, up and down? There aren't a lot of pieces of data here, so it isn't very easy to tell. But it looks like there's no clear slope in both directions. With only 12, this is not always an easy thing. What we're looking for is if we have a picture that is really out of square. Where is it in my picture here? Yes. Page 488. Here are some residual plots. The one on the left is equally up and down, and it isn't tapering in either direction. The one in the middle spreads out as we go from left to right, and the one on the right funnels in as we go from left to right. Now, I don't know where the hell this name comes from, but they call this skedacity. It's all the same, it's homoskedastic. Skedastic. This is heteroskedastic, it's increasing. This is heteroskedastic, it's decreasing. I'm never going to use those damn terms again. But the question is, if the errors are tied to something related to X, I will see a pattern more like these two here. If the errors are independent of X, which is what I want, I'll see a pattern more like this one. So when I look at the residual plot, what I'm really looking at is, hey, do you think there's some difference in the residuals? Are the residuals bigger when your order is bigger? Are they smaller when your order is bigger? In this case, I think the answer is no to both of those questions. I think this looks pretty uniform in its behavior. It's not spreading out or funneling in. All right. If we saw a problem, that would change my confidence intervals. That would change my error estimates. I would do that separately. But in this case, it's fine as far as I can tell. So we have two other pictures up here. What are these? Well, this one, the normal probability plot, is looking at percentile behavior. Wait a minute, percentile. I've heard that phrase. Oh, right. Quartile, decile. We broke it up into 100 groups and then tried to figure out where we would be relative to a percentage. Does that look kind of like a straight line? There's a little bit of wiggle, but it's not all that horrible. This indicates to me that these errors are normally distributed. The closer this looks to a straight line, the more I can say, yes, my errors are normally distributed. There isn't some hidden underlying variable that I didn't know in my correlation. This is referred to as a normal probability plot. It's also called a QQ plot, quantile versus quartile plot. This is the only textbook that I've heard refer to it that way. I've always seen it called the normal probability plot everywhere else. I could also make a histogram of my standardized residuals and look to see how uniform that is. But this, by the way, actually does something similar. And it plots both my residual, and the red boxes are the actual predicted values. So now I can visualize the residual. The residual is the distance between the red dot and the blue dot for each vertical pair. Notice that as I go from left to right, sometimes the predicted value is above, sometimes the predicted value is below. If I go back and I look at my residuals, I can see that my residuals, some of them are positive, some of them are negative. It is quite often useful to look at the sign changes, one after the other. So let's look in order from top to bottom in that list. Do we change sign every other one? Do we change sign every 3, every 4? Is there a pattern to the sign changes? Again, if there is, then it is possible that we have non-independent errors, and the error somehow depends on the one before it. If we flip errors every time, we went negative, then positive, then negative, then positive, then negative, then there has to be something going on that's causing that variation every single time. But here I see, I go from negative to positive, then I got 4 negatives, a couple positives, another negative, and 3 positives. There doesn't seem to be a flip back and forth every time. That, by the way, is called first order autocorrelation. We can look at far more autocorrelations. I know statistics is difficult. I'm sorry, whoever it is. See, they're unhappy about it. The fewer changes we have, we call that a positive autocorrelation. The more changes we have, we call that a negative autocorrelation. If there is positive autocorrelation, then there's some sort of cyclical underpinning going on. Sales data is seasonal. Okay, let's look at that in line with making seasonal adjustments. It'll end up on the sound recording even more so. This is going to be an interesting one when they try and close caption this one. Questions about residual analysis, because really, I can't do this manually. Walking through all these calculations by hand is damn near impossible, and generating this behavior without the computer in front of me, I'm lost. But I could get this information and then go, okay, what does it tell me? What questions do you have? Yes, ma'am. For this, I'd have to give you a picture like this and say, okay, looking at our residual plot, do you see a pattern that is homoscedastic or heteroscedastic? I said I know, funnel out or funnel in here. So I could ask a question like that, but I'd have to give you this plot. Based on this normal probability plot, do you think the error appears to be normally distributed? But literally, I can't ask you to do this calculation unless you've got the Excel open or one of the other statistics programs open. So I have to provide you with this part if we're doing this on paper. And remember, the closer it is to a straight line, the more likely it is to be normal. The further it is from a straight line, the less likely it is to be normal. Nope. I would expect it to be 45 degrees if it was a perfect match, but I doubt it will be. Wow, very unhappy child. He's going downstairs now. She's going to the elevator. This particular example is measuring cockpit noise in airplanes and comparing it to the airspeed of the airplane. If we're traveling faster, is the cockpit noisier? What would you think? Probably it makes sense. So we did a regression calculation. What do you see in this regression information that tells you whether or not noise is related to speed? Notice I didn't even make a scatter plot, just went right to the regression information. Kayla, this is the sort of question. Here's the information. What does it tell me? We did a regression. You could come up with a regression equation. That equation is here. What is the equation? Our slope is this 0.076 number. Our intercept is this 64. So noise level is 0.07 times speed plus 64. Wait a minute. That means for every increase in speed, noise level only goes up 0.07 decibels. That is a really small slope, isn't it? So the faster we go, we get louder, but just a little. Huh. Again, here are my residuals. I start taking a look at all of these residuals, and I say to myself, look at these numbers. Oh, there's something that's unusual. No, that's a regular residual. I need to look at the standard residuals. Here we go. Are any of these unusual? Oh, there's one. I've got one number that's bigger than 2 right here. Another one that's bigger than 2 here. I don't have anything that starts with a 3 or a -3. There's no outliers to this data. I wonder if it's normally distributed errors. So I can look at my normal probability plot. You'll notice a bunch of these have the same noise level, don't they? So they didn't quite get that nice, neat line. And it doesn't look like it's going to 45 degrees. It's kind of lower than that. But that's still pretty linear, isn't it? Very step-ish because it's discrete data, not continuous data. But that's okay. Okay, I think my error is normally distributed. Here's my residual plot. Spreading out, funneling in, or straight? Looks pretty straight to me. There doesn't seem to be any sort of, what do they call it? Heteroscopy, whatever the hell it is. No sort of spread in either direction. I could even go so far as to plot them in order. This is each residual in the order we wrote it down. So as I go from left to right, as our airspeed goes up, I look at the residual between the predicted and actual. And do you see a lot of the same sign or a lot of switching of signs? Wait a minute. Here's 0 right here in the middle. Couple negatives, couple positives, couple negatives. Okay, this doesn't seem to be flipping back and forth with any regularity, does it? So I would say that it's not out of line for that either. This is a good, small autocorrelation behavior. I didn't actually draw the scatter plot, so let's draw the scatter plot. Insert, scatter plot. Okay, here's my scatter plot. Here's my trend line. I'm not even bothered to put any of the equations or anything. There's the line itself. If we have a particularly large outlier, a large residual, something that's way out of whack, it would skew our predictability. It would cause a dramatic change. Now notice that speed here is on the bottom. When we go back and look at the regression equation, the y-intercept was 64. There's our y-intercept. And that would mean that if the plane was standing still, we would expect a noise level of 64 decibels. 64 decibels is not all that loud a room. I'm okay with that. But when I go back and I look at the picture that it just created for me, why should I be pissed at this picture? Oh, I'm all the way back in chapter 3. Well, I'm happy about that part because, you know, we said as airspeed goes up, we should be increasing, but there's a problem with this picture. This picture is all sorts of screwed up. Way back in chapter 3, I asked what was wrong with certain types of graphs, what was wrong with certain types of pictures. Did all sorts of things about things being out of scale and out of whack. Look at the y-axis on this graph. There's no zero. The y-axis is starting at 80. No wonder this graph looks so steep. We said the slope should be 0.07. It should be barely increasing. I need to fix this axis to make this work better. Format axis. Let's make the smallest part of the axis 0. Okay. That makes a lot more sense now, doesn't it? As airspeed increases, my noise level increases, but just a little bit. Now that's more obvious. And I see how tightly those are clustered around my line. Nothing is very much of an outlier. I feel better having this agree with my residual analysis. There is another way to calculate how far out a particular value is. It's called leverage. But the way you calculate leverage is to use your standardized residual and do a really complicated calculation. Now, I must tell you that when I tried to look for a way to do leverage automatically in Excel, it doesn't. So I'm not going to make you do this calculation. I can give you the formula out of the textbook. I don't think it's helpful. But I can tell you what a high leverage piece of data looks like. And to me, that's more important. A high leverage piece of data, these are visual outliers that look weird. Here, on page 493, is our leverage calculation. You see that big formula for H up there? Yeah, forget it. I don't want to deal with it. But what it measures is it measures calculations that are way far away from the average X value because they indicate something that is going to move our line a lot. I need to be close to this line with this dot to have the residual be small, right? So if that line, that dot changes at all, it's going to bring this whole line to a different place. Moving this 1 because it's so far out, changes a lot. Now, they actually tell me that when leverage is above 4 divided by however many things you've got. In our problem with the airplane speed, we had 61 different values. What's 4 divided by 61? I say, I think that's the other way. 0.06. Okay, you did 10. Okay. Now my average leverage should be about 0.066. So anything that's way bigger than that will be unusual in leverage. 4 times that would be 0.25, 24-ish, right? So I start looking at my leverage calculations, and they're all pretty damn small. 0.05, 04, 03. Oh, there we are. 0.069, 0.089. Those are bigger than what we expected, but they're still not too big because they're within 1 over n. I was talking about 4. I don't see anything bigger than 0.25 yet. None of these calculations are high leverage calculations. Whereas if I did the leverage for this would be very big. This particular leverage in this case turns out to be 0.44. And this leverage turns out to be 0.37. Much larger than I would have expected from the actual calculation we just came up with. They should be around 0.06. But even if I don't do any of the calculation, leverage looks like pieces that are way out on the ends that would be in one variable outliers in X, exerting torque, twist on my system. A lot of these are referred to as influential data points. If you've got high leverage, you're an influential data point. But again, that comes from what I can see here in the scatter plot. And in our scatter plot for the airplane noise, we didn't see any high leverage behavior. If I had a plane like a Cessna, whose airspeed is around 100 to 120 knots, that would be way down here, wouldn't it? I would expect the noise level to be a lot different, wouldn't you? But if we're going that slow, we're in a smaller plane with a different type of fuselage and a different type of insulation, the noise might not be related to any of these at all. It says right there, aircraft models were 727s. I used a Cessna. Should we do any measurement like that on here? Wouldn't be an appropriate piece of data. It wouldn't be right for this survey. I don't know where you're going to do these types of surveys in your future job, but somebody is going to ask you, is any of this really out of line? Is any of this really one piece of information that's overly influencing, that's why they call them influential data points, our analysis? Questions? Yes, ma'am.
So contacts like all the plots for like normal probability, what are our options next?
So with something like this, I would say, oh, this does appear to be in mostly a straight line. I expect that my error is normally distributed. If you see something that doesn't look like an increasing line from left to right, oh, I got some up here, some down there. I got some decreasing as I go from left to right. Okay, I think my error is not normally distributed and is somehow related to X. That's a problem. Other questions? If we had another week, The ideal thing for me to do is say, all right, when we did this analysis, we said R square is 0.89 here. 89% of my noise level variation is due to variation in airspeed. What's the other 11%? What other factors are involved here? When you build a regression model, you're trying to tie together these two ideas. In our case, airspeed, noise level. But noise level probably depends on more than just airspeed. We did study hours, right? Exam score related to study hours. But I could ask, what else is your exam score related to? Lots of other factors, right? It would be ideal if I could make a more complicated regression model that took more factors into account. This is called multiple regression and is what a lot more financial analysis does. In particular, I was looking at a project by one of the data analytics students last week, and they pointed out that buy and sell indicators in the stock market can be traced to the last 2 weeks' performance, but it can also be traced to historical performances beyond that. And there are several different models. What if you took all of those models and somehow averaged them together? Could you get a good prediction of a buy or sell indicator? Well, I said, are these models related to each other? Are they correlated to each other? So if we had multiple factors, like we had a 2-factor ANOVA versus a 1-factor, maybe trying to tie two things together, I could do a multiple regression where I said, not only does your exam score depend on the number of hours you studied, it depends on the number of different days over which you did those hours of study. Somebody who studies for 10 hours, all of it on Monday because our exam, all of it on Tuesday because our exam is Wednesday, is probably brain dead by the time they get here on Wednesday, right? But if you study for 2 hours on Friday and 2 hours on Saturday and 2 hours on Sunday and 2 hours on Monday and 2 hours on Tuesday, you've still done 10 hours. But you're probably not melting your brain because you spread it out more. So I could now ask for a regression that compares not just your exam score to how many hours did you study, but also compares it to the number of days over which you did that study. I could tie in more things, more factors, and build more complicated regression models. Best part, all of that is doable in here. It's doable in lots of statistics programs, Power BI, DataViz, the Megastat program that comes with the electronic version of this textbook. And I know for a fact that Dr. Burns is going to talk about this when you all take Quant Biz next semester, BU 451. It is one of the big pieces that follows this course. So I'm not going to cover it, but I think it's worthwhile, and I know you'll see more of it, but that means this is going to be the necessary prerequisite to that. And that's why I needed all this ANOVA crap before it. I needed the descriptive statistics and the standard to build up to where you can make good predictive decisions for your business environment. I promise, I'm making it so I've teed up the ball so that you can knock it out of the park next semester as well. Questions? Monday, I'm going to talk to you about any question you want to ask me about the final. I also would like to ensure that you have done your student evaluation. So bring your computer. I'll give you some in-time class to do course evaluations if you haven't done them yet, but we'll do that. So bring your computers or technology or however you get on Canvas. I will see you all on Monday. Have a wonderful day.